So now let us see that here. Okay, let's continue with this one. So here what we have shown here is the barrier potential. And currently I have not connected any power supply here from the P to the N region, and we have the depletion region well intact and completely occupying around 1/10 of a micrometer. Now let's do one thing. Let's start biasing this PN junction and let's see what happens. So we will see later why are you calling this PN junction as a diode. But anyone knows why you are calling PN junction as a diode? What do you mean by a diode? पीएन जंक्शन को हम ऐसा डायोड क्यों बोल रहे हैं हम? Or in other words, how do you define a diode? When will an electronic device qualify itself to be called as a diode? Okay, so it appears that no one is aware of it. Okay, so we will see that any electronic device will be qualified to be called as a diode if it freely allows the current to flow in one direction, but does not allow the current to move in the other direction. Such a device is called as a diode. And in the process of explaining this whole concept of semiconductor PN junction, we will see that this device qualifies itself to be called as a diode because it's going to allow the current to flow from this P region to the N region, but not in the reverse direction. And hence it is called as a diode. Now, in order to make it into a diode, now we'll be doing certain small changes here. One is that we are going to add a metallic contact. Okay, so this is a metallic contact on both sides of the PN junction so that you can effectively connect it to some, biasing, like a positive terminal or a negative battery like that. Okay, and this is the simplest symbol of a PN junction diode. So every electronic device has a particular symbol. And what does this symbol represent? This symbol represents that the direction of the arrow shows the direction in which the current is going to flow when this PN junction is going to be forward biased. That means when I connect it like this, positive here and negative here, we will be calling the PN junction as forward biased because P region is connected to the positive terminal of the battery. That is why we will be saying it is, forward biased. And here the negative terminal is connected to the N region. Okay, so this whole thing is called as forward biasing. And we will see that when you connect things in this way, the direction of current will be from the left to right. And this arrow mark precisely talks about this only. The direction of the current when the PN junction is forward biased. So this symbol is important to be remembered. In fact, we have some objective questions where you could be given symbols, different symbols, and you'll have to recognize the symbol. Because there are going to be many electronic devices which we'll study in this chapter, like photodiode hoga, then there is going to be Zener diode, then transistor, and many other devices like that. So all of them have different, symbols. So we should not get the symbols mixed up. Okay, चलो यहाँ से आगे जा सकते हैं. So one side is called as a cathode and one side is called as an anode. So which side is cathode and which side is anode here? Can anyone help me out in that? Left side को anode बोलोगे या right side को आप anode कहोगे? Anode is left, huh? Okay. Okay, so anode is left, fine. And this means that this side is a cathode. How do you remember this? इसको कैसे याद रखेंगे वो जरा एक छोटा सा बाद में देखेंगे थोड़ी देर के बाद. Let's see that. So as I have told you before, the direction of this arrow mark, it's basically indicating the direction, the conventional direction of current when the diode is forward biased. Okay. So that is what this arrow mark indicates. Show the previous slide. Okay. So that was the previous slide. Many times at least I often tend to get confused with the anode and cathode. कौन सा side anode है, कौन सा side anode है. So I was thinking, very small shortcut to remember that, which I will show in some few slides ahead. We will put that forward. So first, let's see that what's going to happen to the barrier potential. So we know that this is the barrier potential, which is there, where this is the P side and this is the N side. So if you are connecting the positive terminal of the battery to the N side, it effectively means that you're raising the potential on this side because the positive side is connected to the P side. You're effectively raising the barrier potential or you're decreasing the barrier potential. So when the barrier potential is decreased, it means that the depletion region also, what you see here, has decreased in its width effectively. It has decreased, and this decrease is going to help all the holes and all the electrons on these sides to overcome this potential barrier very easily, because now they will not require so much of kinetic energy. Electric field कम हो गया है, so they can easily cross over, and that is why now your diffusion current will increase. What about the drift current? How is the drift current going to get affected because of this type of forward biasing? Anyone can comment on that part. Effect of drift current due to the forward biasing. Drift current is due to what? Drift current is due to the thermally generated carriers in the depletion region, which are being pushed by the electric field. So as I expected, some students are thinking that this drift current is going to decrease. Okay, so probably they are thinking that electric field कम हो गया तो शायद वो decrease होना चाहिए. Maybe the thought process was correct, but that's not what happens actually, because ये जो thermally generated carriers होते हैं ना, ये पहला तो कम नंबर में है, दे आर नॉट वेरी लार्ज इन नंबर, और उनको पुश करने के लिए कुछ ज्यादा इलेक्ट्रिक फील्ड की जरूरत नहीं है. मिनिमम भी इलेक्ट्रिक फील्ड रहा वो काफी है उनको पुश करने के लिए. सो दिस फॉरवर्ड बायसिंग व्हाट यू अप्लाइड हियर has absolutely no effect on the drift current, because the thermally generated carriers in this depleted region, they are happy as far as the electric field which is reduced is concerned. They can still cross over and go on the other side. So drift current is absolutely not going to change. That's going to be constant. That's going to be constant, and only the diffusion current will increase. So can I say that now there is going to be a net current? Previously when it was kept in the cupboard, then there was no net current, but now because of this forward biasing, your diffusion current has increased and your drift current is constant. So there is an effective current flowing from the P junction to the N region. Okay, so someone wanted to see the previous slide. So that was the previous slide. Okay, so is it copied? ओके चलो, ये वाला भी एग्रीएबल है. Mohit, that why drift current will be constant? Shreya? उसके बाद as I spoke some time back, the some points which I told are written out here, that due to the forward bias condition, the potential on the P side is raised, and hence the height of the potential barrier is decreasing. Or trying to put it in another way, we can say that whatever voltage you have applied, most of that voltage is actually going to apply across the depletion region, because high resistance region जो है हमारे पास वो depletion region है. ये जो P region और N region ये high resistance region नहीं है. So most of this applied voltage is going to come across this junction, and that is why the barrier potential will decrease. That's what we have put here in the first 2 points. That's another way to understand this whole thing, that why the barrier potential is decreasing. All right, Shreya. Okay. Yeah, so she's saying yes. So then we can go ahead in this. So these are just showing different values. Depending upon the magnitude of the forward bias applied, you could change the barrier potential. Okay, that's a very simple diagram, nothing new in that. So the whole result of decreasing the barrier potential, as we have stated before, is that the net current is going to increase. That also we have seen. A lot of theory writing here. Okay, चलो ये वाला भी fine, ठीक है. Now let's talk a little bit more in detail about the forward biasing out here. So here we have a PN junction diode which you have forward biased, and what I'm showing here in this diagram is the electrons that have been injected on the P side uh, from the N side, which is basically called as minority carrier injunction. Because when the electrons come to the P side, what do they form? They form the minority charges. So that's why it's called as minority carrier injection. आप इंजेक्ट कर रहे हो माइनॉरिटी कैरियर्स को दोनों साइड में. यहां पे आप देखेंगे होल्स यहां से डिफ्यूज हो गया है, और ये जो होल्स है, these are your minority carriers here. So you can see here that near the junction there is going to be an increase in the amount of concentration of these minority carriers, isn't it? That's what you're seeing here, कि जंक्शन के बाउंड्री में यहाँ पे माइनॉरिटी कैरियर्स का जो कॉन्सेंट्रेशन है ये इंक्रीज हुआ है. एंड व्हाट्स गोइंग टू हैपन देन, द सेम प्रोसेस ऑफ डिफ्यूजन. यहां से इलेक्ट्रॉन्स डिफ्यूज होंगे और यहां से होल्स डिफ्यूज होंगे बिकॉज ऑफ द डिफ्यूजन प्रोसेस. बिकॉज कॉन्सेंट्रेशन ग्रेडियंट जब भी होगा तो डिफ्यूजन तो होने ही वाला है, एंड दैट्स हाउ द इलेक्ट्रॉन्स विल come out here and come out of this metallic terminal and come out here. Okay, so holes, electrons will come like this and holes will come like this, and then the circuit is completed and you'll have a net current now happening in the circuit. Okay, I hope this part is clear. You can take it down and we'll go ahead. Now, the magnitude of this current is typically in the range of milliampere. The magnitude is important because we will also be reverse biasing the diode. So if you reverse bias this thing, then the current is not going to be in milliampere, but it's going to be in microampere. So that is why we have noted this value, that ये जो range होगा current का, ये milliampere range में होता है because of the forward biasing. So when you plot a graph of the current versus applied voltage, the current axis will be plotted in terms of milliamperes. Okay. So some few points which we have stated are written here. But what is the most important point in this slide is that the current which is injected in the forward bias, ये आपके forward bias में है, that is in the range of milliampere. Now let's see the reverse biasing. So when you reverse bias the PN junction, because the resistance of the P and the N regions are very small, this entire potential will get applied across the junction. So previously, if the potential barrier was like this, the potential barrier is effectively going to increase because of this applied potential. It's going to increase this potential barrier. So when the potential barrier is increased, it effectively means that your depletion region here is increasing in width. And if the depletion region is increasing in width, then your electric field here is also going to be stronger. And that is going to further decrease the diffusion current. So the holes on this side and the electrons on this side, they will find it very difficult to cross over. But there is no opposition whatsoever to the minority carriers which are generated in the depletion region. Because now if there are electron hole pairs generated due to thermal process in the depletion region, then as before, it's not that the drift current is going to increase or something. Drift current is going to remain same. Because small electric field or a large electric field, it's not going to affect in any way this whole drifting happening out here. So all the holes are going to be pushed towards the left and electrons are going to get pushed towards the right, and you will get your drift current as before. So when your diode is reverse biased, we can say that the drift current becomes larger compared to the diffusion current. So it's just opposite to what you saw in forward biasing. And this means that there is a net current. But however, this net current is not going to be in the range of milliampere, but it's going to be in the range of microampere. Because drift current is due to the minority carriers which are thermally generated, which are not going to be too much in number. And therefore, this current is effectively going to be in the range of microampere. Okay. Anand Joshi, is this point clear? Regarding reverse biasing and why the current is in microampere and why drift current is greater than diffusion current? I don't know. Anand is not hearing. Okay, so Anand nahi sun raha hai. Sahi, are things clear here? What we are stating here? I don't know. When did you come in? Okay, चलो सही saying yes. आनंद जोशी को कोई तो बताओ कि जरा सुने, लेक्चर सुन रहा है कि he is hearing or no? Drift current is increased or drift current is decreased? Now I told you that drift current is going to remain same, but diffusion current is decreased. So drift current becomes greater than diffusion current because diffusion current is decreased because of this increased potential barrier. That is why the drift current becomes more than diffusion current. It's not that in reverse bias drift current is increasing and diffusion current remains like that only. Is it declared officially that our boards are around April? That you have to confirm from your principal only, because that SB college principal told that it's going to be in the month of April, but I don't know, on what basis he told that. So please confirm that from your school. You're thinking something else when we are teaching this. Okay, so Mohit, is this all right? This is clear that drift current does not change at all, and diffusion current decrease hota hai. Okay, so these points we'll just put forward here. Uh, the effective barrier is increased, and because the effective barrier is increased, it suppresses the flow of the majority carriers. That means your diffusion current decreases. That's what I mean by this statement. And the electric field, however, is going to aid the minority carriers, in being swept across the depletion region. So drift current is going to remain as it is. Okay, it will be same in magnitude. Okay, chalo, isko le lo aap. Okay, going ahead now. As I've said before, the drift current is going to be a very small value. It's going to be in micro amperes. So 10 raised to minus 6 amperes. And that is because this current of drift is due to the minority charges. And this minority charges is very less. So that is the reason why it's in microamperes. See, drift current is also there in the forward bias. But at that time, it is very small compared to the diffusion current. So that's one thing. So drift current is there in both cases. Diffusion current, however, we will say is very, very less when you are doing the reverse biasing. So that's one difference, how the drift current and the diffusion current behave when you forward bias and reverse bias your diode. So here we have plotted the VI characteristics of the PN junction. So VI characteristics means the plot of voltage applied across the diode versus current. You can see that in the forward biasing state here, in the upward direction, we have shown the current in milliampere. And when you're reverse biasing, I'm interested in the microampere range. That's why here at the bottom is written in microampere. The right side of the potentials indicate the forward biasing of the PN junction, and the left side indicates the reverse biasing of the PN junction. Now, some few points which we would like to, first take an observation, and then later on we can discuss, what could be the probable reasons for those phenomena. So first thing what you see here is in this region, what comment do we have about the drift current? ये क्या है ये current? ये drift current है. ये वाला रिवर्स बायसिंग के केस में तो आप देख सकते हैं कि ड्रिफ्ट करंट इज अप्रोक्सीमेटली कांस्टेंट. जो मैंने पहले भी कहा था कि ड्रिफ्ट करंट इज नॉट गोइंग टू बी अफेक्टेड इन एनी वे by the increasing or the decreasing potential applied across the PN junction. But one thing which we observe here, which we will have to discuss at some later point today, is that there is a certain potential called as breakdown voltage. यहाँ पे VBR लिखा हुआ है, VBR. BR stands for breakdown. So there is a certain voltage in the reverse direction which could be applied to the PN junction, where suddenly we observe a very large current which starts flowing. And the voltage, the reverse bias voltage at which that happens is called as the reverse breakdown voltage. So why this breakdown happens, we will discuss that in brief later, sometime later today. But first, let's make some observations. So two observations we have made here. The drift current is constant initially, independent of the reverse biased potential, and then suddenly after the breakdown voltage the current can take on any value, but the voltage remains constant. So if the PN junction is operated in this region, in what application could it be used for? This circled region which I'm pointing now. Suppose if I make the PN junction operate in this range, then can you think of any application of the PN junction in that region after the crossing of the breakdown region? Anyone would like to offer some application? Harsh, you remember something about this region? See, what is the characteristic of this region? Current can take on any value, but voltage remains constant. So that is the main clue. Current can increase to any value, but your voltage remains constant. So what can it be used for then? Voltage remaining constant. उस डिवाइस को क्या बोलते हैं हम इलेक्ट्रॉनिक्स के टर्म्स में? Unfortunately, what happens is that nowadays you don't see that device. When we were small, that time we used to have that device explicitly on top of your fridges, on top of your television channels, your TV set, and therefore it was easy for us to relate. But nowadays all those devices have got integrated inside the fridge or inside the TV, and therefore we don't see those devices. But if the voltage is kept constant irrespective of how much our current flows, we call such a device as a voltage regulator. वोल्टेज रेगुलेटर का मतलब है कि चाहे जितना भी करंट बढ़े, but the potential across the load will always remain constant, and that is the application of a voltage regulator. I do not know how many of you all have heard of this term voltage regulator. जब आप कोई फ्रिज या ये खरीदते हो तो उसमें लिखा रहता है कि कितना वोल्टेज रेगुलेशन वो प्रोवाइड करता है, ये सब चीज लिखा रहता है. I do not know how many of you all have read all those features. Okay, so we will discuss in some time more in detail of the application of a PN junction as a voltage regulator, but that's a little bit later. Another thing what you see here is that when your diode, your PN junction is forward biased, up to 0.6 volt, there is no current. And after 0.6 volt, there is an exponential increase in the current. So there are four observations totally we have made here. One is that in the reverse bias state, the current remains constant, or the drift current is constant in spite of increasing the reverse bias voltage. And the reason for this, we are already aware. We have already discussed this, that as you increase the reverse bias voltage, there is no reason why the drift current has to increase, because drift current is due to the minority carriers in the depletion region, and they will drift irrespective of whether you are having lower reverse bias voltage or higher reverse bias voltage. It's not that if you decrease the reverse bias voltage, lesser minority carriers will drift, because the electric field is sufficient for pushing all the minority charges formed in the depletion region on both the sides. So this reason we have already seen before only. Now, can anyone offer an explanation for this part? That why the current is zero in this region, even though you are providing some forward biasing of 0.6 volt? So I don't know, Prathamesh Chaudhary is there here. So if he can throw some light on that fact. Prathamesh Chaudhary, are you hearing what I'm saying? Can you offer some reason for this region? Okay, so someone else is saying this, that when you're forward biasing your diode, I drift equal to I diffusion. Huh? Okay, so so Mohit is saying that I drift equal to I diffusion. Yeah, that is correct in one sense. So when you're forward biasing the diode, let's say that it's unbiased. So if this is the N region and this is the P region, then we know that we have this depletion region here in between. And this depletion region was basically ensuring that the diffusion of the carriers don't take place. Okay, so that's why the current is zero here. In fact, drifting does happen, but the value is so small in microampere, and this has been plotted in milliampere. That's why you don't see anything here. It's a flat curve here. Okay, drift current is still there, but we are not showing that drift current here because it's been plotted in milliampere and drift current is in microampere. So that's not going to take on any value here. And the current is not going to flow till the time you ensure that this electric field is brought down to certain value, because this electric field is preventing the holes and the electrons to cross the barrier, isn't it? So unless you bring down the electric field, you cannot expect the holes with a certain kinetic energy to cross over the barrier. So that is the reason why up to a particular forward bias potential. So when this is added, we know that previously it was like this and now it will decrease. Abhi, when it decreases, then after decreasing to a particular value, then these holes and electrons will have sufficient kinetic energy to cross the junction. So that is the reason why here you don't see any current. The current is approximately zero. Though it is not zero, huh? Actually it's in microamperes because drift current is there in this region. Is that fine explanation that why this part is there, uh, Omkar? Uh, okay. Now we have to talk about this region. So by looking at this region, what do you feel? Does the PN junction follow the Ohm's law, or is it a non-linear device? By looking at this particular region, which I am circling now, does it follow the Ohm's law? It's non-ohmic, okay? It's non-ohmic or it is non-linear because it's exponential in nature. ये जो ग्राफ ये ड्रॉ किया है, ये exponential curve है current और voltage के बीच में, and that is why we say that the PN junction is a non-linear device. So these are certain important things for theory also. Many questions asked in this section are theoretical questions. So there will be four options where theory-based questions will be there. So we have to be careful regarding all these small points here. So it does not follow the Ohm's law. Okay, so we can go ahead now. And whatever we explained, let's put all of those things in words here. So the current under the reverse bias we see is essentially independent of the voltage up to a critical reverse bias voltage called as the breakdown voltage. This we already know the reason. This reason we have not seen yet, but which we'll explain in some time, that when the reverse bias voltage becomes equal to the breakdown voltage, then we see that the current is increasing sharply. And there are applications of the PN junction in this region. But normally, the PN junction is operated only in this region. This is the region in which the PN junction is operated. In this region, you'll operate it only if you are planning to use it like a voltage regulator, not otherwise. Okay. So in this region, we observe that slightly if you change the bias voltage, एकदम slightly, large change in the current is there. That's what you observe here. And you need to be careful that your device does not get damaged, because when so much of current flows, there could be a lot of heating which will happen and your diode could get damaged. So there has to be external protective circuitry, and also this diode should be capable of taking that much amount of heat. So when you fabricate it, there are certain cares that we have to take care, especially when the diode is going to function in this region, or even in this region same thing will happen. In this region also current is very high, so your diode could be damaged. So you will have to either take care that in the external circuitry you put some resistance to ensure that the current is limited, or else the diode has to be fabricated in such a way that it can take on so much of heat. All right, so you can take this down before we go ahead. So going ahead now, we are talking about the heating effect, that it is important that the manufacturer specified current should never be exceeded. So when you take any diode, then the manufacturer specifies certain limits of currents which that diode can handle. And we have to ensure that the current, whether reverse or forward, never exceeds those limits. Otherwise, there will be overheating and the diode can get damaged. Perfect. Kamlesh, are we on the right track in understanding things? So I just wonder that why you all are not answering. Only some few SB Patil students and Exceed students are all hearing, but SB Patil students, I don't know what they do. They sleep off, I think. So anyway, coming back here, in order to find out the VI characteristic, this is the typical circuit that is used. So here you have a PN junction which is forward biased, and this arrow indicates that it's a variable supply, so that you can vary the forward bias. You can vary the forward bias and change this voltage so that you can see the curve. So that is why that arrow mark is shown there. Or you could use a rheostat. That's another option in the circuit, so that you can change the resistance. And you can see that the current, the ammeter which is used here is a milliampere, because in the forward direction we expect the current to be in the milliampere range. So the voltmeter will measure the voltage across the diode, which will be plotted here, and the current flowing through this will be plotted on the y-axis. In the reverse bias situation, we'll be connecting it in the opposite way and replace the milliampere by a microampere. So these are some few changes if you want to plot the VI characteristics of the diode. So probably I forgot to take this attendance. So you can log off and log in by that time.